Prime number. A prime number is any number greater than 1 and has exactly two factors, 1 and itself. For example, the numbers 2 and 3 are prime numbers since they have factors 1 and itself. Some more prime numbers are 5 and 7. And the number 4 is not a prime number since it has more than two factors as 1, 2, 4. Some more examples which are not primes are as shown on the screen. Composite numbers. Composite numbers are the numbers which have more than two factors, that is the number 1, the number itself, and at least one other number. Examples are as shown on the screen. Note: 1 is neither prime nor composite. We know that all natural numbers except 1 can be written as a product of their prime factors. For example, let us go through some of the numbers. Say 3 is equal to 1 into 3. 6 can be written as 2 into 3. 253 can be written as 11 into 23, and so on. But here 1 is neither a composite nor a prime. Can there be a composite number that isn't the product of the powers of primes? For this, let us take an example of factorizing a large natural number 163800. Let us use factor tree that is well familiar to all. Now, let us have a look on some of the natural numbers. 163800 can be written as 2 into 81900, and 81900 can be written as 2 into 40950. 40950 can be written as 2 into 20475, can be written as 3 into 6825. 6825 can be written as 3 into 2275. 2275 can be written as 5 into 455. 455 can be written as 5 into 91. And 91 can be written as 7 into 13. Here factorization of 163800 as shown. Therefore, when we write the above terms in terms of product of powers of primes, we obtain as shown. Let us try with another number. 1, 2, 3, 4, 5, 6, 7, 8, 9. This can be written in the following form as shown. Here the numbers 3803 and 3607 are primes. By this we can prove that a composite number can be written as the product of primes. Here are some examples as shown on screen. If the numbers taken has all the possible primes, what would be the size of the collection? Will it contain only a finite number of primes or infinitely many? It is infinitely many. Therefore, if we multiply all these primes in every possible way, it produces an infinite collection of composite numbers. The following gives us the fundamental theorem of arithmetic that tells every composite number can be factorized as a product of primes or given any composite number. It can be factorized as a product of prime numbers in a unique way, except for the order in which the primes occur. Take an example for this. Take a number 210 and factorize it. We get product of 2, 3, 5, 7 as same as product of 3, 5, 7 and 2, or any other possible order. By this we conclude that there is only one way of writing the product of primes. Now, let us state the fundamental theorem of arithmetic. Exploring real numbers. Statement of fundamental theorem of arithmetic. Every composite number can be expressed or factorized as a product of powers of primes, and this factorization is unique, apart from the order in which the prime factors occur. Let x be the composite number. Let us factorize it as shown, where x is equal to p1, p2, pn are the primes. If we use same primes, we get all the powers of primes. When the primes are arranged in ascending order, we get it as p1 less than or equal to p2 less than or equal to, so on up to less than or equal to Pn. Then the factorization number is unique. For example, 1,63,800 can be written in terms of product of prime factors as shown. Exploring real numbers. For example, the composite number 2310 is expressed in terms of product of primes as shown on the screen. Therefore, the products of primes are 2, 3, 5, 7 and 11. Now, let us learn how to apply the fundamental theorem of arithmetic on more than one positive number using the prime factorization method. Prime factorization method. This method involves finding the prime factors of a given number. This method is used to find the highest common factor HCF and the least common multiple LCM of the given number. Let us look at an example. Find HCF of integers 12, 18 by the prime factorization method. Solution. Consider the positive integer 12. To find its HCF, express it as a product of 2 and 6. Here 2 is a prime number and 6 is a composite number. Now, the composite number 6 can further be expressed as the product of two prime numbers 2 and 3. In this way, the number 12 is expressed as a product of prime numbers only. Similarly, the expression of other positive integer 18 in terms of product of primes is shown on screen. It is observed that the highest common factor of these three numbers is 6. Therefore, the HCF of the numbers 12, 18 is 6. That is equal to product of the smallest power of each common prime factors in the numbers. Find the least common multiple of 12 and 18. To find the least common multiple of the given numbers, consider the number 12 among the given numbers. It can be written as the product of least common multiple 2. The number 18 can be written as multiples of 2. The number 6 is further expressed as a factor of 2, keeping the other number unchanged. At this stage, the two numbers can be expressed as factors of the least multiple 3. Now, the obtained numbers are prime in nature. They cannot be further factorized in terms of numbers other than 1 and themselves. The product of all these prime numbers is shown on screen as the least common multiple of the given numbers is equal to product of the greatest power of each prime factors in the numbers. Consider the numbers 4 power n, where n is a natural number. Check whether there is any value of n for which 4 power n ends with the digit 0. The number 4 power n does not end with 0 because it should be divisible by 5 or should contain a prime number 5 in prime factorization. But it isn't possible with this, as 4 power n is equal to 2 to the power of 2n, so 2 is only prime in the factorization of 4 power n. As there is no number 5 as prime factor and there is no natural number n for which 4 power n ends with the digit 0. Show that 12 power n cannot end with the digit 0 or 5 for any natural number n. The number 12 power n does not end with 0 because it must be divisible by 5 or 10 and should contain a prime number 5 in prime factorization. But it isn't possible with this, as 12 power n is equal to 2 to the power of 2n into 3. So 2 and 3 are the only prime in the factorization of 12 power n. As there is no number 5 as prime factor and there is no natural number n for which 12 power n ends with the digit 0.